Welcome to Geometry Episode 1 on Euclid's Elements. So it's 300 BC, we're in ancient Greece, and there's this guy Euclid who's just written a 13-volume encyclopedia called the Elements, containing all the mathematics known to the ancient Greeks at that time, most of which happened to be geometry. In fact, what we now call Euclidean geometry. And this encyclopedia was revolutionary because rather than simply present all this information as a bunch of random facts, Euclid provides a logical progression in which one thing leads to something else and something else and so on and so forth, starting right at the very beginning with a collection of postulates which are taken as being self-evident and from which everything else can be derived just simply by logical reasoning. So this, of course, is the prototype for an axiomatic development of a mathematical theory. And it was so successful that more or less every mathematical theory since then has been done in the same way. Now, in this course, Euclidean geometry is going to be the first type of geometry that we look at. We'll be looking at it from a modern perspective, but nevertheless, in order to set the scene, it's really nice to be able to go back and just see what Euclid did, get a flavour for what he did in the Elements. So what we'll be doing is, to begin with, in this episode we'll be looking at Euclid's axioms for planar geometry, and then establishing some notation that we can use, which in fact we'll be taking through most of the rest of the course. And then we're going to take a quick trip through Book 1 of the Elements, which is where Euclid lays out all the properties of triangles. So we'll be cherry-picking a few results from Book 1. So a collection of 3 to begin with, which are SAS congruence, pons asinorum, and triangulation. Then we'll be looking at the triangle inequality. And finally, we'll be looking at some results to do with the area of triangles, Pythagoras' theorem, and the angle sum of triangles. And then right at the very end, we'll be making some observations, which hopefully will provide us with some motivation for what follows. If you want to follow this in the notes, you'll find everything in Chapter 1. Well, Euclid has 5 axioms, which he calls postulates, for planar geometry. Here are the first 2. So as you can see, these have got to do with straight lines. Axiom 1, if you have 2 points, then there exists a unique line segment joining them. Axiom 2, if you have any line segment, then it can always be extended to an infinitely long, if necessary, straight line. Now, by the way, Euclid doesn't really give any serious attempt to define what he means by a point, or indeed a line. So he says a point is that which has no part, and a line is breadthless length. So make of those what you may. The third axiom has to do with circles. So we can draw a circle of any radius we like around any point we like. The fourth axiom, all right angles are equal. And the fifth axiom, this is a rather lengthier one. So if a line falls on 2 lines so that the interior angles on one side sum to less than 2 right angles, by the way, of course, he's introduced right angles in the previous axiom, then the 2 lines meet on that side. So those are what Euclid considers to be self-evident truths about geometry in the plane. So let us make some remarks. So the first remark is that Axiom 1 implies that lines can meet at most once. That's the uniqueness statement. Well, Axiom 3, where it talks about circles of any radius, that introduces us to the ideas of length and distance. which are of course very important in geometry. On the other hand, Axiom 4 introduces us to the notion of angles, in particular right angles. So what does this statement mean? It's a very short statement. It might seem so obvious as to hardly be worth stating, in fact. But what Euclid has in mind here is the following. So if you have a straight line and another straight line which meets that straight line in such a way that the angles here and here are both the same, let's call them alpha. Those are what are called right angles. In fact, right means upright. And if you had another straight line somewhere else, maybe at a different angle completely, which met a line in such a way that these angles were also the same, let's call them beta, so you had these two situations, then what Euclid is saying is that alpha and beta would have to be the same. And we could go one step further and just say, actually, the value that they would take, this common value, we'll denote it by pi over 2. Euclid didn't actually use this measurement, but nevertheless, in hindsight, we can use pi over 2 just as an abbreviation for a right angle. Now, Axiom 5 is the interesting one, shall we say. It's usually called the parallel postulate. What it's saying is the following. If we draw a picture, so we have two lines, and we have a third line, which falls on those two lines, which just means simply it cuts across them, in such a way that the angles, what he calls the interior angles, which are these two angles here, if those angles sum to less than two right angles, then the two lines themselves will go on to meet. So eventually there will come a point here where the two lines actually meet up. And in fact, you end up with a triangle. So if you like, you can think of this postulate as being an answer to a question which arose right at the very beginning with the first axiom, and the consequence that two lines meet at most once. And the question arising from that is, when do two lines meet? And Euclid is saying that in this situation, you're guaranteed that they will always meet. So it's worth pointing out that Axiom 5 is in fact equivalent to another version due to a mathematician called John Playfair. Yes, that really was his surname. Quite a long time after Euclid, came up with alternative version of Axiom 5. Let's call it Axiom 5 dashed. So given a line and a point not on the line, there exists a unique line through that point which is parallel to the given line. In other words, which doesn't meet the given line. So the picture for this is a bit more straightforward. So you have your line, you have a point not on your line, and then there exists a unique line through that point that never meets the original line. Now, one of the great discussions in the centuries after the elements was whether or not Axiom 5, or this equivalent version, Axiom 5 dashed, were in fact independent of the previous axioms, whether you could in fact prove them using axioms 1 to 4. So a lot of work went into trying to, in fact, to try to derive Axiom 5 from the previous axioms. However, eventually it was shown that Axiom 5 is indeed independent. So these two versions are indeed independent. This was shown only as recently as late 19th century by a mathematician called Beltrami. Okay, there's more that one could say about these axioms, but we'll leave it at that. Now let's establish some notation. So Euclid talks about points. So in order to talk about points, mathematically, we're going to denote them by uppercase ABC, line segments. So the line segment joining A and B will be denoted by simply AB, or we could, if we prefer, write it as AB, BA rather. So the order of the points is immaterial. For lines, if I have a line segment, AB, and I want to write down the line extending it, which of course is a consequence of axiom 2, then I just simply put a line on top. Or I could equally well have written BA with a line on top. So again, the direction is immaterial. This line is not an arrow, it's not a vector we're looking at. This is just a straight line, etc. Or, if I want to write down a line without any mention of the points lying on it, I could just simply denote a line by, say, something like L or M. What about lengths? So the length of a line segment will just be denoted by putting bars around it. Or, if I prefer not to mention the endpoints, then I could use notation such as little a, little b, little c, angles. So if I've got a situation where two lines meet at a point A, let's say these other points are C and B, then the angle that they meet at will be denoted by, use the angle symbol here. Again, it doesn't matter which way I write it, provided the point at which they meet is right in the middle. So BAC or CAB, depending on how we feel. Or we could simply denote the angle by a Greek letter. Finally, triangles are very important in Euclid's Book 1 in particular. So we will denote by triangle symbol ABC the triangle whose vertices are ABC. So we assume that A, B and C do not lie on a straight line. So if I have a triangle, so we're going to adopt the following conventions for denoting the various lengths and angles in the triangle. So the angle at A will be called alpha, angle at B will call beta, this one is gamma, and then the lengths of the edges opposite the vertices will be denoted by lowercase letters. So finally, a very important definition. So we say that two triangles, ABC and A dashed, B dashed, C dashed, are congruent, and we denote it by this symbol, if they essentially have all the same lengths and all the same angles. Euclid actually doesn't use the word congruent, he uses the word equal. If I have two triangles with these properties, then he says these triangles are equal. That's perhaps taking a little bit too far, because clearly these triangles need not be equal, but as far as their shape is concerned, they are identical. So now we're going to take a quick look through Book 1 of Euclid's Elements. So I'm going to, in this section, pull out 3 results fairly early on in Book 1 for us to look at, beginning with what Euclid calls what he labels proposition 4. So this is SAS congruence, side angle side congruence. So it's a very familiar result, and says simply that if you have triangles in which then the triangles themselves will be congruent. So you don't need all these measurements to be the same. 3 will suffice, provided they are correctly chosen. So I want to go through the proof of this, and I want to actually state it in Euclid's own words, in effect. But to begin with, let's have a picture. So this is the configuration that Euclid is dealing with. So we have two sides rather, and the included angle. So what Euclid says is rather interesting. So he's imagining moving triangle ABC onto triangle A dashed B dashed C dashed by placing the vertex A on the vertex A dashed and the edge AB along the edge A dash B dashed. So this edge is going to get placed along there. And then he's saying that because the lengths c and c dashed are the same, that means that the vertex b will end up being placed on the vertex b dashed. He then goes on to say, so because the angle alpha and angle alpha dashed are the same, that when you place triangle ABC on triangle A dash B dash C dashed in this way, then you'll also find that the edge AC ends up being placed on A dashed C dashed. And then because these edges B and B dashed are the same, C will end up being placed on C dashed. Then finally, so because when all this has been done, you've placed a triangle ABC on triangle A dash B dash C dashed in such a way that the three vertices have coincided with each other, that implies that the third edge, this one here, will end up getting mapped onto edge B dash C dashed. Again, that's by uniqueness of line segments from axiom 1. So his conclusion, he simply states that the third edges must therefore be of equal length, and that means that the angles which they contain, the two angles, beta and gamma, beta dashed and gamma dashed, will also be the same. Hence, the two triangles are congruent. So there is a remark, in fact there are a couple of remarks that one should make about this. And the first is, really, there is a big assumption that Euclid is making here, something that really comes out of nowhere, certainly not mentioned in axioms at all, which is that it is possible to move one of these triangles onto the other in the way described. So the implicit assumption is that he can move objects around in the plane without changing lengths or angles, in other words, without changing their geometric features. So as I say, that is a huge assumption. We don't know how it's justified. In fact, some commentators have even said that this is such an assumption to make that it really ought to be a separate axiom. And the other comment is that it's only the first, second and third which appear in this proof. So axioms 4 and axiom 5 do not get used to prove SAS congruence. This is a very important result for Euclid, and he uses it time and time again. The first application that he makes, proposition 5, goes under the interesting name of pons asinorum. Of course, pons asinorum is a Latin phrase. Euclid was Greek, so it's been translated. It means bridge of asses, or bridge of donkeys. Why that should be the case is anyone's guess. Your guess is as good as mine, in fact. Anyway, that's what Euclid himself called it. And what it says is the following. So a triangle with two edges equal, of course, is what we would now call an isosceles triangle. So he's saying if you have an isosceles triangle, then the angles opposite those equal edges are also equal. So this proof actually isn't the proof that Euclid gave. It was given by Pappus, who lived considerably later, AD 300 rather than BC 300. And what he says is the following. So let's draw our triangle again. So we're going to apply the SAS congruence result to the triangle ABC, and also imagine it applied to the triangle BAC, which you can think of as being the mirror image, if you like. So SAS will tell us that these two triangles are in fact congruent to each other, because the sides A and B are equal by hypothesis. So these two triangles are congruent because, well, they satisfy the hypotheses of SAS because they share a common angle here, and the two sides, including that angle, are the same. Therefore the triangles are congruent, and therefore the corresponding angles in those triangles must all be equal which means that alpha and beta are the same. So for some reason Euclid didn't like this proof. His proof was considerably more complicated, and in fact it used axiom 4, whereas this proof doesn't. It just uses the axioms that were used for SAS, which are axioms 1 to 3. And in fact there's a danger that Euclid's proof ends up producing a circular argument with something that he goes on to prove later on. The converse is also true, in fact. So if you have a triangle with these angles, alpha and beta are equal, that will also imply that the corresponding edges, the opposite edges, are equal. However, that needs axiom 4. So finally, following those two propositions, proposition 7 talks about triangulation. So in other words, how to find where you are in the plane given suitable measurements from other points. So let's suppose the following. We have a pair of points A and B on a line which we'll call L. We have a pair of points, we'll call them C and D, which are not on L, so they're off L, but they're on the same side of L. And finally, we assume that the distances from these 2 points, C and D, to A are the same as are their distances from B. So given that situation, these 2 points must be, in fact, the same. So their distances from the 2 points on the line suffice to locate them uniquely on the plane. So this is an interesting proof because actually it's proof by contradiction, which of course is a method of proof we've already come across, notably in the proof that the square root of 2 is an irrational number. But here's an example of proof by contradiction being used in geometry. So we suppose for a contradiction that the 2 points C and D are in fact not the same. Then we're going to construct some triangles. So by our assumptions, these 2 lines have the same length, as do these 2. You can see we have a pair of isosceles triangles, in fact, and that means we can plug into the previous result, pons asinorum. So let's have a look at the angle, this angle here. So that angle is less than the angle BDC, which is this whole angle here. But by pons asinorum, that must be equal to this angle here. So these 2 angles are equal in the triangle BCD by the fact that these edges are the same. So angle BDC is in fact equal to angle BCD, which in turn is going to be less than angle ACD. So this angle BCD is less than angle ACD. But by pons asinorum, this time in the triangle ACD is equal to, so this angle here, which is opposite this edge, must be equal to this angle here, which is opposite that edge, which has the same length. So that, of course, is a contradiction. You can't have something which is less than itself, and that proves the result. So a remark which is worth making at this stage is that everything we said so far, this and previous results, only uses axioms 1 to 3. So for our next sequence of results, I want to talk about the triangle inequality. So this turns out to be far more significant than Euclid imagined at the time, and it appears as proposition 20. So in any triangle, the length of one side is always going to be less than the sum of the lengths of the other 2 sides. So that seems remarkably obvious, but of course if you're starting from scratch, then that's something you have to prove. So this proof is a good example of how Euclid uses various constructions that essentially he's justified from his axioms. So we want to compare the sides opposite C and B, the length of those two sides. So what we'd like to do ideally is to put those two sides together in a straight line. So we're going to do that by extending the edge AB of our triangle by an amount exactly equal to the distance B. So that's something we can do by axiom 3. That will produce a point D, which we're going to then connect up to vertex C. Let's call this angle delta. Then, as you can see, we have a triangle with two sides equal, so it's an isosceles triangle, and therefore by Pons Asinorum, the angle ACD, this angle up here, must in fact equal delta. So if I look at the triangle BCD, which is the big triangle, then what I notice is that the angle BCD at the top is the sum of angles gamma and delta is clearly bigger than delta. So in this triangle, this big triangle, this angle is greater than that angle. And this implies that the opposite edges, BD, which has length B plus C, must be greater than the edge opposite vertex D, which has length A. So we're using a property of triangles here that the greater the angle of the triangle, the longer the edge opposite will be. So this follows from a result which Euclid has also proved. So this is proposition 20. He's proved previous to this another result. So we'll just backtrack to show why this conclusion is justified. So a pair of propositions, in fact. So if you have any triangle, then for one edge to be longer than another edge is exactly the same as the opposite angles being greater than one another. So this is like a generalization of the Pons Asinorum situation, where of course you had two edges which are the same, implying that the angles opposite them were also the same. So if they're not the same any longer, then in fact we have this relation of inequality between the angles and the edges. So the proof of this is an if and only if statement, so we have to prove both directions. To prove the forward implication, so since the edge opposite vertex A is greater than the edge opposite vertex B, I could, if I wanted to, construct an isosceles triangle by marking out the point between D, between B and C, such that CD has length B. So I construct an isosceles triangle. Being an isosceles triangle, I can now apply our Pons Asinorum result to it to conclude that so the angle down here is equal to the angle at D. Therefore, so alpha is greater than delta because simply alpha is this angle here, whereas delta is this smaller angle here. However, delta being this angle over here, this is the exterior angle for triangle, this skinny triangle, ABD. So if you have an exterior angle of a triangle, then that angle is always going to be greater than either of the two opposite angles. So in particular, it will be greater than the angle beta. Now this is a result that we haven't yet shown, but Euclid has already proved this in the previous proposition, so we're going to have to backtrack once more, which we will do after we finish the proof. So we proved the forward implication. Now let's prove the backward implication. So this is just a very careful, clever application of logic. If I combine the result I've just proved with Pons Asinorum, I can insert an equal sign into this equality. Because I know if A and B are equal, then alpha and beta will also be equal. So in effect, I've actually proved this pair of inequalities. And then I take the contrapositive of this implication. So you remember what that is. So I take the conclusion and I negate it. And that implies the negation of the premise. And then I simply relabel. And there I have the converse. Alpha greater than beta implies A greater than B. So by the way, Euclid presents this result as in terms of inequalities. However, with the benefit of hindsight, we know exactly how these different angles and lengths are related to each other by what is called the Sine Rule. So the Sine Rule gives the precise relationship between angles and their opposite edges. But in Euclid's time, that wasn't known. In fact, Euclid didn't know anything at all about the trigonometric functions, sine, cosine, all the rest of them. So he wasn't able to actually state the Sine Rule, but he just gave these inequalities. So we're going to have to continue backtracking for a little bit longer. So the proposition that we need now to prove is Euclid's proposition 16, which deals with exterior angles of triangles. And it says, so the exterior angle at vertex A is greater than either of the interior angles at the other two vertices. So again, this is a clever proof using a construction technique. So the first thing I'm going to do is find the midpoint of the edge opposite, say, vertex B. Let's call that midpoint D. I'm going to then create the line from B through D and keep going until I reach a point equidistant from D to B, but on the opposite side. So this is going to be called point E. I then join E to vertex A, and let's also extend the edge AB out a little bit. So what you should see in this picture is two congruent triangles. But before we go into that further, let's just summarize our construction. Okay, so the exterior angle that we're going to look at is this one here. So that is the angle pi minus alpha, which we can see is greater than this angle here, and this angle is in fact equal to this angle because the two triangles, this one and this one, are congruent by SAS. So we've shown that the exterior angle here is certainly greater than the angle gamma, one of the angles opposite it, and then you can guess probably that in order to show it's bigger than the other angle, then all we have to do is to make a similar argument. So I look at the median from C this time, and that'll tell me that exterior angle pi minus alpha is also bigger than the angle beta. There. Okay, so a nice little sequence of propositions culminates in the proof of what turns out to be a very important result in geometry, not just in Euclidean geometry, but all sorts of geometry, called the Triangle Inequality. A couple of remarks. Firstly, we're only using the first 4 axioms for this proof. We're not using Axiom 5. And something else which it might have occurred to you that in fact what we're looking at here, these angles, pi minus alpha, beta and gamma, Well, if I know that the sum of the angles of the triangle alpha, beta and gamma are in fact pi, then it must follow that pi minus alpha in fact is equal to beta plus gamma. So it's not surprising that this inequality should hold, but of course we haven't yet proved that the angle sum of a triangle is pi. So that is something which, with hindsight, we could derive using that property, but of course we haven't got it yet, and as we'll see, the property of the angle sum actually requires the fifth axiom. So by doing it this way, we're actually showing that not all the axioms are necessary. But nevertheless, let's make the remark so the final set of cherry-picked results from Book 1 are these: the angle sum formula for a triangle, the area formula for a triangle, and Pythagoras' theorem. So the first of these occurs as proposition 32. So what Euclid does here is invokes the fifth axiom, the parallel postulate, to draw a line through one of the vertices, let's call it vertex C. So he constructs the line L through the vertex C, which is parallel to the edge AB of the triangle. This, of course, is using Axiom 5, or in fact Axiom 5 dashed. And then he uses some facts about angles between parallel lines. So because L and AB are parallel, this angle and this angle must be the same. So this angle here must be alpha. Similarly, angle beta must be the same as this angle here. So these are what we sometimes call Z angles. And of course the angle here is gamma. And also the fact that if you have angles on a straight line, they're called supplementary, they always sum to two right angles. So again, that's another fact that Euclid proves earlier. So the facts concerning Z angles and supplementary angles tell us that alpha plus beta plus gamma, in fact, is equal to two right angles, in other words, pi. So that's very simple and straightforward. It's probably something actually you've come across before when you've proved this at high school. So shortly after having proved the angle sum formula, Euclid moves to the area formula. So this is a little bit more wordy because he doesn't have quite the same apparatus that we have today. So what we'd like to say is something like the area of triangle ABC is equal to half BC sine alpha, but he doesn't have the trigonometric functions available to him, so he has to put it in a slightly different way. So what he says is, so the area of a triangle is half the area of any parallelogram on the same base with the same height. So again, if we construct a line through this vertex which is parallel to the opposite edge, so we're thinking of AB as being the base of our triangle, then if I have any parallelogram on the base AB, let's say this one here, with these edges, then the area of that parallelogram is twice the area of the triangle. In particular, the parallelogram could be a rectangle, and that would give us the area formula straight away. So we won't prove this, but suffice to note that, as you can see in the picture, again we've used the parallel postulate to construct our parallel line L. So this is a common theme for all the results in this final section. They all use Axiom 5. So the final result is the most famous of all, perhaps, concerning triangles, which is this occurs in penultimate place in Book 1 of the Elements. It's the penultimate proposition, proposition 47. So I don't need to tell you what that means. However, the proof that Euclid gives is quite interesting. So you're probably familiar with a proof using similar triangles. That's what we might call the standard proof. In fact, it was known for several centuries before Euclid, using this precise proof. Now, Euclid was quite reluctant to use it, in fact, because maybe he had in mind that using similar triangles would be a routine which involves looking at ratios, and there was this uncomfortable fact floating around even in Euclid's time, although it had been discovered several centuries before, that the square root of 2 is an irrational number. So the Greeks were not very happy with irrational numbers. So rather than getting involved in this minefield of irrationality, Euclid decided to use a completely different proof of his own devising, in fact, which involved only areas and congruent triangles. So this is how it went. So the first thing that Euclid does is to construct the squares, the geometric squares, on the sides of this triangle. So that'll suffice for the purposes of showing the idea of the proof. So what he does now is he constructs the line through A parallel to the edge CV. So because AW is parallel to CV, and because this angle is a right angle, it follows from the parallel postulate that this angle must also be a right angle. In other words, we have a rectangle, CDVW. Now the clever thing that Euclid does is to construct two new triangles by joining the vertex A to this one right up here, V, and the vertex B to the vertex of the square right up here. So we construct the line segments AV and BY. So we have two triangles that we need to pick out. That triangle, so the triangle BCY and the triangle ACV. So these two triangles are in fact congruent by SAS. So two of their edges are edges of the squares. You have two edges which are edges of the small square. So this edge here and this edge here. And then two edges of the big square. This edge here and this edge here. And then the angle between those two edges, which in this triangle is that angle, and the other triangle is this angle, so those angles are in fact the same, because they share this little piece in common, and the other bits are both right angles. So by SAS congruence, these two triangles that we picked out are in fact congruent. And one consequence of that which Euclid appeals to is that congruent triangles, since they have every aspect of their geometry the same, must also have the same area. But what is that area? Well, by the previous proposition, so for the triangle BCY, we can see that actually has the same base, CY, as the little square, and that little square has the same height as the triangle. So by the previous proposition, the triangle must have half the area of that square. In other words, the area of the square, which is little b squared, this is the edge, little b of the triangle, so that is twice the area of the triangle BCY. And then by the congruence that we've just established, that must be exactly twice the area of the triangle ACV. So triangle ACV has the same base, namely this side here, as the rectangle CDWV. and therefore it must have half the area of that rectangle. Okay, so in a similar argument, we can show that the other side of the right-angled triangle, this one down here, so that's the square we haven't drawn, but if we were to draw that and repeat the argument, then we would obtain that c squared, in fact, is the area of the other piece of the square on the hypotenuse. So this rectangle here. So that's the rectangle BDWU. Then all we have to do is to add these two equations to get b squared plus c squared is the sum of the areas of these two rectangles, which is simply the area of the square, which is a squared. So in summary, I think nobody would disagree with the fact that the elements is undoubtedly one of the greatest achievements of Greek mathematics, if not mathematics of all time. However, it's not beyond reproach. For a start, it relies very heavily on drawing pictures. So in modern mathematics, although we do like pictures, we don't really want to use them as proofs. We want to have a proper, rigorous proof, which doesn't involve a picture. It could also be argued that Euclid's axioms are rather vague. And then, of course, there was this assumption that Euclid made about isometric motion. So the ability to move around in the plane in such a way that angles and lengths are not changed, in particular moving one triangle onto the other to prove the congruence result, which is a vital, as we've seen, it's a vital tool in more or less everything that follows. So this assumption is huge. So those are sort of on the debit side of things, but on the positive side, so Euclid understood triangulation, and that also is a tool or a property that we're going to see is very important when it comes to putting Euclidean geometry in a modern context. And then it's worth pointing out that the triangle inequality and various other properties that it depends on doesn't use Axiom 5. So what we're going to be looking at ultimately are geometries which share axioms 1 to 4 of Euclid but don't have Axiom 5. So in these geometries, because the triangle inequality doesn't use Axiom 5, we might expect it to still hold. However, so the final three results that we've just proved do use Axiom 5, which means that in a non-Euclidean geometry, we would expect those results to change. Okay, so that is as far as we're going to go with this introductory episode. So I'll sign off for now and look forward to seeing you next time.